The world is full of data. Every app that you use is full of data. On Khan Academy, we store data about users and badges and progress. On Facebook, they store data about who you are, who your friends are, what they're posting. On Bank of America, they store data about how much money you have and what accounts that's in. How do these apps store data? Well, they use a database, which is a program that helps store data and provides functionality for adding, modifying, and querying that data, and doing that all fast. Databases come in many forms, but a really popular type of database is called a relational database. It stores each kind of data in a table, which is kind of like storing data in a spreadsheet. A row represents an item, and a column represents properties about that item. For example, to store data about Khan Academy users, we'd have a users table with a row for each user and columns for properties like their nickname and location. Relational databases make it particularly easy to form relationships between tables. For example, in order to store Khan Academy users and their badges, we might have a users table and a badges table, and then a user badges table to remember which users earned which badges, just by mapping user IDs to badge IDs. That's a more efficient form of storage than having to repeat everything about the user and everything about the badge in the user badges table. Most databases come with a query language to interact with the database. SQL is a language designed entirely for accessing databases and is the most popular of them. With SQL, we can create tables, change data, get back to data that we're interested in, like we want to find out which users joined in the last week or which users have a particular badge. That's what we're going to teach here, and you'll actually get to try out SQL here in the browser using SQLite, a particular implementation of it. You won't be able to write the whole app here, but when you're done learning SQL, you'll have a much better understanding of how data is stored in the apps that you use, and be able to use SQL if you ever build an app. Welcome to my database. It has no data in it yet because I want to build it up with you. What sort of data should we store in our first table? Let's start with a grocery list, which you've probably used in real life. I'm pasting an example list, which has 3 delicious items and how much we want to buy of each of them. Our first bit of SQL will be the command to make the table to store this list. I'll write create table in all caps, and then the name of the table, groceries, and then parentheses and a semicolon. We see an error pop up because the SQL interpreter expects to see column names inside these parentheses. What column should we have in order to describe each item on our list? Well, first we need a name for the item, which I'll call name, and we need to follow that with a data type. We have a few options. Let's go for text. If we look on the right-hand side, we can see our new table is listed with 1 column. But we also need to specify how many of each thing to buy, like our 4 bananas. So let's add a quantity column as well. And this will always be a whole number, so let's use an integer for that data type. And now we can see that new column listed in our table. That looks pretty good if we're thinking about what data we have in this grocery list, but we're missing something that we need in databases, a unique identifier for each row. We almost always need unique IDs for each row in a database because we need a way to identify rows later when we're updating or deleting them and not be dependent on other columns because those could change. We typically specify this ID column first, so I'm moving my cursor before name. I'll call this column ID, that's standard, and then for the data type, I'll have to write this phrase, integer primary key, which signals to the database that it should treat this as the row identifier and that each row must have a unique value for this column. Okay, now we have our groceries table with 3 columns in it. It's empty though, so let's put some data in it. We'll write insert into, and then the table name, groceries, then values, and then parentheses, and here we start listing the column values in the order that we declared the columns. The first column was ID, so I'll put 1, since we haven't used that ID yet. The second column is name, so I'll write bananas. And the third column was quantity, so I'll write 4. Do you see how the schema updated on the right? It now says that there's 1 row in the groceries table, so our insertion worked. Let's add the next 2 items and just doing the same thing. Insert into groceries, values, 2 peanut butter. I want just one of those because otherwise I eat too much. And insert into groceries values in ID 3. Dark chocolate bars have to be dark. Milk chocolate is not even chocolate. And we'll get 2 of those. Okay, so it says 3 rows, but to really see that the database actually contains data, you can click the table name on the right. This will insert a select statement in your code. And don't worry too much about this now because we'll get to it in the next video. If you want, you can pause the talk through and try clicking the table name yourself to see what happens. That's it. That's all we needed to create our first table and add data to it. It's pretty cool, huh? In the next section, we'll see how to get the data back out of the table in more interesting ways. We're back with our groceries table, but we've expanded on it a bit. It now has a column for which aisle number we can find the item at the supermarket, plus we've added a few more items. Now you can really see the power of SQL in different ways that you can retrieve data from your database. And this is also where it can get a bit tricky. To start off simple, how would we retrieve all the rows from our table? To perform any query, we write select, and then which columns we're interested in, like the name, and then from, and the table name that we're selecting from. And we can see a list of the groceries on the right under that results section. But what if we want all of the column names? We can just replace name with star. And that was also the query that got inserted when you click the table name, which you might remember from the first talk through. This list is out of order though. If we went from top to bottom at the store with this list, we'd have to keep changing aisles. We'd rather have it ordered by aisle so that we can be more efficient at the store. To do that, we can just add an order by clause to our query, specifying which column we want to order by. That's better. Now we can get our ingredients faster. But to be even more efficient, my brother and I like to shop together and split the store so that I shop in half the store, he shops in the other half, and we meet at the checkout. There are 12 aisles at this grocery store, so for my list, I just want to know which items are in aisles 6 through 12. Well, anytime we want to filter results out, we can use a where clause for this and specify the column name and then what we want to compare it to. So in this case, I used a greater than operator, but there's lots of different comparison operators depending on what it is we're trying to filter by. Great. So now I know exactly what items I'm going to get. I'm going to be really efficient. And you've learned a few ways to use SQL to query. Now stay tuned to find out even more ways that you can select. We're back with our grocery list. I can see that it has 6 rows in it, but I can also see that we need to buy more than one of each item, like our bananas. So I'm not sure offhand how many items we'll end up buying total. And I'd like to know that total number so that when we're cashing out, we could just do a quick check to see if we have the right number of items in our cart. Well, to do that in SQL, we can use what's called an aggregate function. An aggregate function is useful for things like getting the maximum, minimum, sum, and average of values in our database. In this example, to get the total number of items, we'll start with select, then the name of the aggregate function we'll be using, sum, then the name of the column we want, and then from the name of the table we're selecting from. Ta-da! So we can see on the right that the sum is 15, so we should have 15 items in our cart if we got everything correctly. And notice if I go up here and change the number of bananas, because I'm going to invite my monkey friends over for a jungle party, we can see the sum increase in real time and get bigger and bigger, so we know that we're now going to need 67 items in our cart. Now we could easily try out other aggregate functions here, because sum's not the only one. So if we wanted to know what is the most that we'll be buying of any one item, then we could use max. See, 56. Those are obviously our bananas. But this information is useful for this case. Let's go back to sum. Okay. Now what if we wanted to make sure we had the right number of items after each aisle? Well, we can do that in SQL using the group by clause. We add it to the end of a query, specifying the column name to group by aisle. Okay, so now we can see that in one aisle we have 9, another of 1, but I don't actually know which aisle we're getting each of them in. So what we can do there is just add aisle to the beginning of this select. So there you can see, okay, so we're going to get 9 items in aisle 2, 1 item in aisle 4, 56 in aisle 7, and 1 in aisle 12. Awesome. Now, how did that actually work behind the scenes? The SQL engine first did the grouping of the rows based on aisle. So first did this group by, then it summed up the quantity in each of those groups, and then finally it selected the first aisle value that it saw in each group. And, the aisle value was the same for all of them, so we got the aisles back out. But we could have also said name here, and we do see a name for each of the rows, but it's a bit misleading because for some of these aisles, there are actually multiple items in that group, but the SQL engine just picked the first item out of it. So you really shouldn't be using something different from what you're grouping by because you might not get a sensible result. So we'll say aisle, and now that's an accurate presentation of our data. Okay, so great. You've seen aggregate functions, you've seen group by, and now you can efficiently gather useful statistics on your data. Another tool for your SQL toolbox. I've spent the last few talkthroughs making a grocery list. Well, now that I've realized how much eating I do, I realize what else I should be tracking in a database. How much exercise I'm doing. So I'll start by pasting in some statements that create a table and insert a few rows of data. Let's see what I have in exercise logs. We have an ID, of course, a type, which is a string like biking or dancing, minutes for how many I spent, calories for how many I burned, and heart rate for how high it went. Now I'm inserting the data using a slightly different syntax than before. Notice how I'm specifying the column names in parentheses after the table name. When I do that, it means that I don't have to specify every column value here. I only have to specify the ones that I give in this list of column names. Now, do you see which one I didn't specify here? The missing column is ID, and that's very much on purpose. ID, here we go. The ID column is the primary key in the table, and it's set to auto increment. That means that the database will automatically fill it in for us when we tell it to, by picking an ID that's different from the other rows in the table, usually a number that's 1 bigger than the biggest number so far. Now, I would rather have the database figure that out than have me figure it out. So I usually like to do my inserts this way, leave out the ID, let the database do that work for me. Okay, so there we go. My database table is set up, and it looks like I've even done a bit of exercise. Go me! Let's find out where I'm burning the most calories with a simple query. I'll just modify this one. So select from exercise logs where calories greater than 50, and we'll just order by calories as well. Okay, so I've done 2 activities where I've burned more than 50 calories, and it looks like dancing burned the most. Now, I want to find out which activities I've done that have burned more than 50 calories, but also taken less than 30 minutes, because I want to exercise more efficiently in the future. It's pretty obvious from looking at the current results. There's only 2 results. It's easy to look at that. But just imagine that there are thousands of rows. Maybe this is data from thousands of users. I would need a way to filter that down in the SQL query itself. To do that, I can use the AND operator to combine those multiple conditions, like to only return the rows where calories are greater than 50 and minutes are less than 30. Haha. So now I only see one result, dancing, which means I should just spend my whole life dancing, which sounds pretty good to me. Okay, so in a similar way, I could use the OR operator to return rows that meet any of some conditions. Like, let's say rows where calories are greater than 50 or heart rate is above 100. And that helps me find the most vigorous exercises. Now we can see that dancing and biking are both good, and actually, I do like biking. It's just a bit harder. Now, you can have as many OR and operators in your query as you'd like. The AND operator has precedence over the OR if you've got both of them in the same query, but you can always use parentheses to change the order of evaluation, just like with math expressions. Now I want you to try these out in the next challenge, and stay tuned for the next talk through where I'm going to show how to do some interesting things using this type column here. See you then. I'm back with my table of exercise logs, and I've added a few more rows. Now, if I wanted to filter these logs to just show my biking logs, I could just add where type equals biking. Simple. It's getting sunny outside, so actually what I want to find is all of the outdoor activities, not just biking. So to do that, I can use the OR operator that we just learned, checking each of the different outdoor types. So type equals hiking, or type equals tree climbing, or type equals rowing. Unfortunately, I don't yet have a mountain or a tree or a lake in my home, so all of these are outdoor activities. All right, so that worked, but there is actually a simpler way to do this query, and that's using the in operator. The in operator will check to see if a particular value is in a list of values. Let me show you. So we'll take this query and I'll paste it, and then I'm going to replace this equal sign with in, and then put a parentheses, and then I'm just going to separate each of these strings with a comma instead of that whole long or type equals blah. Ta-da! Same results like we expected, but this query is easier to read and it's a bit shorter too. We could easily also do the inverse query if we just want to see the indoor activities. We just write not in. So that's just dancing, and I'll save that for the winter time. Let's change it back to in and our outdoor activities. And I'm going to show you something a little more interesting that we can do with in. First, I'm going to need another table of doctor recommended activities. I'll paste in the SQL for that. Let's see, where do we have it? Here. So here we've created a table of doctor recommended activities, which just has a type, which matches our type from up here, and a reason, which is why the doctor recommended it. Now, what if I wanted to see all my exercise logs that correspond to doctor recommended activities? Well, first, I might want to see what are those doctor recommended activities. So select type from doctor's favorites. Okay, biking and hiking. So I could just take this query and modify it and just shorten it to biking and hiking. However, if the doctor's favorite tables changed, like there was a new row added or a row deleted, then this query would be out of date. What I want is for this query to always be up to date with what's in this table here. So what I can do is use the in operator directly with the results of a SQL query, a select query. And it's actually very simple to do. I'll replace what's in the parentheses with the query that we did before. Ta-ta! Cool. So we call this inner query a subquery. It's the query that we're doing inside the outer query. And now this query will always pull based on whatever's in the doctor's table at the time. It will stay up to date. And this is a pretty simple subquery, but it could actually get really complex. It could be as complex as any of the queries that we've learned so far. Let me show you an example. What if we only want to select the favorites that the doctor recommended for cardiovascular reasons? So we could say where reason equals, and then we could paste this whole long reason in here, and we see hiking. But what if for some reason we didn't have the period in here? Well, now we actually see nothing for that query because it's trying to do an exact match and it can't exactly match that. So there are times like this when we want to do an inexact match, and we can do that with the like operator, which is a pretty neat operator. And so to do it, we're just going to take this and I'm going to replace the equal sign with like and get rid of, because all we care about is that very important word cardiovascular. That is what we're looking for. So we say cardiovascular and we also put a percentage sign on either side, which acts as a wildcard. So this should match any rows which contains the word cardiovascular anywhere, and it did. Yay! Okay, so that's pretty cool. Whew. We covered a lot in subqueries like. Hopefully you're pumped to try them out in the next challenge, or take a break, go climb a tree, and come back. Either way, I hope you have fun with it. Let's continue with more queries of my exercise logs. Let's say that I want to see how many calories I've burned for each type of activity. We can do that with an aggregate query. Say select type and then sum calories from exercise logs, and then we're going to group by type. Now I can see each type with how many calories I've burned total for that type of exercise. Now, do you notice how the column shows up as sum calories in the results? If we want, we can actually tell SQL to give that column a new name just by writing as and then giving it the new name total calories. That can make our results easier to read, and it also has another benefit, which we'll use later. So next, I want to filter the results to only show activities where I've burned more than 150 calories total across all the times I've done that exercise. It turns out that 150 calories is the amount in 1 ounce of dark chocolate, so it seems like a good amount to shoot for. Now, my first instinct might be using where to filter. Like if I took this query here and then said where calories greater than 150, then we only see dancing and we don't see biking, which we would expect to see. The reason we only see dancing is because it filters each individual row that comes in. And dancing is the only exercise where I burned more than 150 calories in a single log. But what I want to know is which exercise type or types have I burned more than 150 calories across all of the logs for that exercise type. We actually have to use something new for that, which is the having clause. To use that, we'll remove this where, and then after the group by, we'll write having, and then total calories greater than 150. Ta-da! Now we see biking, because now it's actually looking at the total calories, and I've indeed earned more than 150 over time in my logs. So as you can see, those two queries are actually different, but they are easy to confuse. When we use having, we're applying the conditions to the grouped values, not the individual values in the individual rows. We could use any aggregate function on a grouped column that makes sense. Sum, min, max, average, whatever we want to check. Let's do another example. So if we want to see the average calories for all the exercises where we burn, let's say more than 50 average total. Oh, that's all of them. So let's up it. 100 in the middle, still doing good. 70, cool. So you can see we can play around with that query there, get different results with that having. Now let me do something a little different. Let's say we want to see all the exercise where we logged at least 2 activities for that type of exercise. For that, we're going to use a count function. So I'll select type from exercise logs, group by type, and then having count star, doesn't matter what column, so we can just do star, greater than or equal to 2. Okay, so now we can see biking, dancing, tree climbing. I've done all of those at least 2 times. Makes sense because those are my 3 favorite activities in life. Besides coding, of course. Okay, so now you've seen having. Remember that it's easy to confuse having with where when using these aggregate functions. So think through your results and make sure they make sense. And now you get to try it yourself. Let's try a few more advanced SQL features. I've been logging heart rate for each of my exercises, and I haven't done anything interesting with this data yet. So now it's time. I did a little research on the internet, and I found that the maximum heart rate is 220 minus your age. So one thing I can do is query my logs to see if my heart rate ever goes above max, since that would be pretty scary, or tell me that there's something wrong with my heart rate checking device. Okay, to do that, I'm going to do a count star. So count star from exercise logs, and then where heart rate greater than 220 minus my age, 30. Woohoo, there's no results, and that makes my heart happy. Now, notice I'm using the subtraction operator, and in fact, I can use most math operators in SQL, like to add, subtract, multiply, or divide. And if I need to, just like in math, I can throw in parentheses and change the order of evaluation. All right, so we've confirmed that my heart doesn't go above max. That's good. Now let's look to see if my heart gets into the target heart rate zone. And that is 50 to 90% of max. So we're going to start with our count star, and we just need to change our where. So this time we're going to say heart rate is greater than, and let's look at 50% of max. So that's 220 minus 30. Okay, so you see I'm combining a few math operators here. And I'm going to also throw in the round function just to show you that we can use that function. It's pretty nifty. And then we're going to say and I'll just copy paste this and change it to less than 90. Let's go ahead and throw a equals in there. All right, so now we're checking to see 59% of max, and we see there are 4 logs that fall in that target zone. But what about my other logs? What zones are they in? We don't know. All we know is that 4 of them are in that target zone. The rest could be maybe they're 90 to 100%, maybe they're less than 50%. What I would really like to see is a summary of all my logs and how many were in each of the heart rate zones. Now that sounds like a situation where I would use a group by, like group by this column that says which heart rate zone this row is in. But I don't actually have a column like that to group by. Well, I can effectively create a column using the case statement. Now I'll admit that I find this the trickiest statement to use in SQL. So I struggle with it a bit, and don't worry if you find it a bit odd as well. It's similar to an if or a switch from programming languages, if you're familiar with those. Otherwise, don't worry about it. All right, so I'm going to use case, but I'm just going to start with outputting what we know, which is type and heart rate from exercise logs, and see what that looks like. Okay. Now, for each of these rows, I want to add a new column that says which zone the heart rate is in. To do that, I go into the select part of the query, and I'm going to write case to begin the case statement. Then I type when, and the first condition, which is checking if it's above max. So that was heart rate greater than 220 minus 30. Then I write then, and an expression, which is just a string. So we'll say above max. Okay, so this is my first case. Now I'm going to keep going with my other conditions. So when heart rate is greater than 90, then we'll say it's above target. And then, so if greater than 90, and then we'll say at that point, if it's greater than 50, we can say it's within target. And everything else would be below target. So I could do another condition for that, but I can also just be lazy or smart, however you want to think of it, and say else below target. Okay? Now, my conditions are all done, but I haven't told SQL what to name this new column. For that, I write end as HR zone. Awesome. So now for each of the rows, I can see the new column with a nice description of what zone they're in. Now that we've done that, finally, I can make a query that summarizes how many of my logs are in each of the zones. And that is a whole lot easier now that I've set up this case. I'm just going to take this query here, copy it, and I'm going to group by the new column we created, and then add count star, get rid of the heart rate, see what we have here. Aha! And now we see that we've got 4 below target and 4 within target. That's pretty neat, huh? That case statement, it is a tricky one, but it sure is handy once you get the hang of it. You may not use it all the time, but it's good to know just in case. I've set up 2 tables in this database. A students table with detailed information about each student, like their name and email, and a student grades table, which has their student ID, test name, and grade. Let's see what happens if we just select everything from student grades. Ta-da! Okay, so we see student IDs, test names, and grades. I'd actually rather be able to see student names, emails, that sort of thing. Now, what you might notice is that the student ID in student grades is related to the ID in students. So this 1 here is actually referring to Peter Rabbit, and this 2 here is actually referring to Alice in Wonderland. Now, I want to form a query that will output the student name and email next to each test grade. And that information is in 2 different tables. So that means I need to join the tables. And there are a few ways that we can do that in SQL, and we'll try them all out actually. The simplest is called a cross join. And I can make that happen just by putting both table names after the from. Ta-ta! So as you can see, lots of rows. And basically what this did is that for each row in the first table, it created a row for each of these rows here. That means we end up with 8 rows because it creates 4 rows for each of these 2 rows. This is the simplest join, but it's also the least useful. We don't want every row matched with every other row. We only want them matched if the student ID matches. Now we can do that using an inner join, which isn't actually much more work at all and is way more useful. So there's actually a few ways of doing an inner join. We'll start with just building off the last query, and we can add a where. And the where will check to see that the student ID matches student's ID. All right, so now we actually have what we wanted, is test grades next to names, because it's done the cross join and then just limited to the rows where those columns were the same. Great. This syntax here is called an implicit inner join, and it works, but it's not actually the best practice. The better way is if we do something called an explicit inner join. And that is using the join keyword. So to do that, we're going to start with just doing from one table. And actually, I'll do from students and then join on student grades. And then instead of where, we do on. And that specifies what columns are being matched. So on students.id equals students grade dot student ID. All right, so now we have the same results as before. Switched, but really the same. Now that I have these tables joined, I'm just going to whittle down the columns I'm outputting to the names, the email, the test name, and the grade. Okay, beautiful. Now, the cool thing is, once we've done joins, we can still use where and group by and all those fancy things. Like, let's say that we want to filter down the results to just grades greater than 90. Woohoo! Let's see. Oh, no. Grade. There we go. Haha. Lots of ones above 90. Now I can email all those students with a high five. Okay, but what would happen if my tables both contain columns with the same column name but different meanings? Like right now, our student grades table has a grade column. Well, what if my students table also had a grade column for their overall class grade? That would mean down here, when we selected grade, it wouldn't know which table to pull it from because there'd be a grade column in both of our tables. So actually, to be super safe, we should prefix our columns with the table name that they're from. So we say students.firstname, students.lastname, students.email, studentgrades.test, studentgrades.grade. Okay, now we know that we're going to get the columns from the table we expect them to be in. Great. Now that is our basic explicit inner join, and it is what you'll use for most of your joins across related tables. But if you stay tuned, I'll show you a few other types of joins as well. I'm back with my related tables about students, with the students and the student grades, and I added a new table to keep track of what projects students are working on. And once again, this one has a student ID to relate it to the students table, just like the student's grade had. And it also has a title for each project. Now what I want is a list of student names and the projects they're working on. So that means I need to join student projects with students. We can do that, as you probably guessed, using an inner join that we just learned. So what do we want? So we want students.firstname. We want students.lastname. We want the title of the project, so from the students projects table. And then we'll say from students, join student projects, and on students.id equals student projects.studentid. All right, so I see one project, Peter, and his very promising Caratapult experiment. But where is my other student, Alice? Well, we're missing Alice because an inner join only creates rows if there are matching records in the two tables. There's no row for Alice because there's no row in student projects that has Alice's student ID in it. And this makes sense, and oftentimes with joins, we do only want rows where the records matched. But in this case, we want a comprehensive list of every student and their project, and we want every student to be on that list, even if they don't have a project yet. And that is where an outer join is super useful. And it's really easy to use. We're just going to go right here and type left outer. Ta-da! Now we see Alice, and there's a big old null for the project title. Okay, so how this works is that the left tells SQL that it should make sure to retain every row from the left table, which is the one after the from, students. And the outer tells it that it should retain the rows even if there's no match in the right table. which is student projects. And that's our outer join. And there's a lot of cases where you might find you want an outer join. And just keep in mind that the behavior of inner versus outer joins. There are also some other sort of outer joins. There's a right outer join, and it basically does the opposite, is make sure that it keeps everything from the right and then joins with the left. We don't actually support right outer joins here, but if you want that, you can just switch the table order and it's the same thing. So you don't actually need to have a right outer join. You can always use left outer join. And there's also something called a full outer join, and that matches rows, if it can, on both the left and the right side, and fills in nulls when it can't on either side. And that's pretty interesting, but also is not supported in our environment here. And that is one of the interesting things about learning SQL. I'm showing you lots of things that work here and work in other SQL environments, but every environment is a little different. So you'll constantly be tweaking the tools in your SQL toolbox for each new environment. And that's true about a lot of things with computers, honestly. You'll learn the general techniques and then learn how to adapt it for a specific language or app or environment. And you basically just get really good at learning. So, yay! Let's say that we want to create tables to store the data for a diary app. A basic setup would be a users table and a diary logs table. Now, when a user wrote up their diary on the website, we would have some code to execute an insert statement like what I'm pasting in here. So this inserts 2 rows for 2 diary logs, one day after the other. First, where somebody has a horrible fight and buries their woes in 3 pounds of dark chocolate, and the next day, of course, they make up and celebrate with ice cream, as you do. So we can check to see what our diary logs table looks like now, and we can see those 2 posts in there. Now imagine that the user comes back and wants to modify their logs, maybe because they don't want to admit, even to themselves, that they have eaten that much dark chocolate. Now, we've already inserted the data, so at this point, we would need to have code that would execute an update statement like this. Update diary logs set content equals I had a horrible fight with Ono's guy. Now, this is telling it to update that table and set the content, but it's not telling which row to update. We need to tell the database which row to update because we don't want it updating every row with that content, just one row. So how do we find the log to update? Well, we can use the ID like that. If we didn't know the ID, we could also filter by columns that we knew were unique to the log, like user ID and the date. It was 2015 0401. But really, if you know the ID, it's safer because you're not relying on having to filter on columns, which could actually be the same across multiple rows. If you might have a diary app where users are allowed to write multiple logs per day. It really depends on how the app and the tables are designed. I'll go back to the ID since I know the ID. Now we can do another select to see that our table changed. And it did. No more knowledge of those 3 pounds of chocolate. Okay, so the user made that change, but then the user decides that they actually want to delete the entire log entry. Like maybe because they want to forget that they even had that horrible fight. So in that case, we would need to have code to execute a delete. So we can say delete from diary logs where, and once again, I'm going to use the ID because I know it. And let's select again to see what it looks like. Haha! So we only have 1 row left, which means that our delete worked. Now, you should be very careful whenever you're doing update or delete because you want to make sure you're updating the actual rows that you intend to update. You don't want to update the wrong rows or delete the wrong rows and lose that data. In fact, some apps never issues deletes. They never really delete rows. Instead, they add a deleted column to their database, and then they'll do something like deleted equals set deleted to true when the user wants to delete, and then they filter based on deleted equals false in the select queries, something like that. So that means that you never actually delete data, which can be a little bit safer, but it's a little more complicated to do that as well. So anyway, that's up to how you design the app. So now with select and insert and update and delete, you have all of the commands you need to handle what a user would want out of your diary app. And now hopefully you can better imagine which commands are happening behind the scenes when you use your favorite apps every day. We're back with the database for our diary app. Now, when we first created these tables, like the diary logs table, we decided to store user ID, date, and content. And now I want you to imagine that a few months after we launched this diary app, a user designer suggests adding a "How are you feeling?" drop down on each diary entry. And the user would say something like happy or sad or confused. In order to store that, we need to add an emotion column to the table. Now, we could just add it like this, but if this was a database for an app in a real production environment, then we couldn't just edit the create statement because that's something that we actually issued months ago and it's already happened. And if we rerun it, it'll actually remove the current data. And we don't want to lose all the data that we've gotten over these many months. So at this point, after we've done create and after we've got data, we're going to need to use the alter table statement. And to use that, we write alter table and then the name of the table, and then add, then the name of the column name we're adding, and then the data type of that new column. Great. So now the next time that the user makes an entry, we'll need to specify that column, or we can specify that column. So let's say, all right, let's say they went to Disneyland, and to specify that new column, we're going to put comma emotion, and then here we'll just say happy. Most people are happy that go there. Okay, so let's see what it looks like now if we select it all. So we can see the latest row has happy in the emotion column, and the row before it has that big old null in it. And that is what databases usually do. They fill in null for unspecified values. If we want, we can actually get it to fill in some other value for rows where it wasn't set, and that's what we think of as the default value for a column. So to do that, if we had wanted to do that, we would have put default and then the value in that alter table statement when we ran it. So now you can see instead of null, we see unknown. So that's an option for you when you're adding a column, and just something to keep in mind, depends what you're adding to the database. Okay, so now let me show you something that you rarely do, deleting an entire table. Maybe I would do this if I migrated all the data out of this table into some new table, or if I just got mad and decided to be a horrible person and take a rampage all over a database. That's bad. But anyway, we can do this using the drop table statement. And now if I try to select, what happens? I actually get an error because my table no longer exists, so it can't select from it. So that was a bad idea, and I'll just delete it. You should think really carefully about dropping tables. Do not just drop them willy-nilly. You should also be careful with alter table, especially if you're running it on a table with a lot of rows, because you can have performance issues there. Really, I don't want to scare you, but you should be careful whenever you're making any changes to your database. With great power comes great responsibility. And now you have both. I'm back with just the table about students this time. I've added one more column to the table, buddy ID. See, I decided that every student should have a buddy, somebody that they can pair up with, do assignments with, study with, all of that. Now, the buddy ID is what it sounds like. It's an ID that relates to the ID of the student that they're buddied up with. So, for example, here, Peter is buddied up with 2, and 2 is Alice. Let me just do a select that should make that more clear. So select the ID, first name, last name, buddy ID from students. Okay. The interesting thing here is that this buddy ID is a column in a table that's related to another column in the same table. That's a bit different from before, where we'd have columns related across different tables. So, what if we wanted to show the names of each student next to the email of the buddy? Not just the ID, the email. To do that, we need to actually join the students table with itself, because the 2 bits of related data that we need both happen to be in the same table. We can do that by, let's see, so we want the first name, last name, email. So to join students with itself, we're going to write from students and then join students. Okay. All right. Okay, so we get an error. First name is an ambiguous column. And that's true. We're telling to select first name, but it's joining across 2 tables, and both of these tables have the same column names. And before, we would just prefix these with the table names, but we can't do that here because actually they're both named students. So we need to give it a way to distinguish between this one and this one, even if they're kind of the same thing. And we can do that by giving one of them an alias. So we're going to write the alias right after here. The alias is like a nickname. So here's the alias, buddies. And then we just have to specify that the email is coming from buddies.email. Haha. There we go. Now we're seeing too many rows, way too many rows, and that's because we don't have an on clause yet. So it's just joining every possible row with every other one. Now our on should check that the buddy ID from the students table, that first one, matches the ID from the second table, buddies, or what we called buddies. Haha! Now we can see Peter with Alice's email address, Alice with Peter's, etc., etc. To make this results table even a little more clear, I'm going to rename buddy's email as buddy email. Okay, so now it's a lot more clear that we're looking at Peter Rabbit and his buddy's email. Cool. Now this type of join is called a self-join, and that's because it's a table being joined to itself. You can try this out in the next challenge, and I'll show you one more way to use self-joins in the talk through after. I hope you'll join me. If not, just join yourself. Now I want to show you a combination of joins and self-joins. So this time I'm back with multiple tables, tracking the students and their projects. Now, since I have students working on great projects, I want them to review each other's work in pairs. For example, hyena habitats should review carpet physics. That's why I've created this new table, project pairs, and all it stores is 2 project IDs that are paired with each other. Now, let's see. What do I see if I select star from project pairs? Okay, it's just a bunch of numbers, a bunch of IDs, all the IDs that are mapped with each other. It is not the most human readable output at all. What I'd like instead is rows of project titles paired with each other. The project titles are in the student projects table. So that gives me a clue that I need to somehow join project pairs with student projects. Let's see what happens if I do that. Aha! So now we see project IDs and project titles in each row. What I eventually want in the results table is to see 2 project titles in each row, not just one. So that's another clue that we need to do another join, a self join of student projects with itself, so that we can get those same column values twice. Now, it may not be obvious how to add a self join at this point because we already have a join. If we want to add another one, we can actually use the join keyword again. So join student projects, and we need to make sure we give them different aliases so that they're not ambiguous. So A and B. All right, so now we've got a lot of stuff in this results table, but if you'll scroll, you'll see that the project titles show up twice in each row. So maybe let's make it easier to see. A.title, B.title. Great. But we still have way too many rows because we're matching every row with every other row, and we haven't added the on clause, the very important on clause. So we're actually going to add 2 on clauses, one for each of the joins. So on project pairs, that's project 1 ID equals A.ID. And then on project pairs dot project 2 ID equals B.ID. Aha, there we go. So thanks to this combination of joins and self-joins, we can see a nice list of project titles paired with their project title. Now, you can use as many joins in your query as you need to get the data that you want, but generally, more joins means slower queries. If you're interested in how to figure out if your queries are slow and making them more efficient, we'll talk about that soon. So stay tuned, keep at it.